Hey everyone, this is Javier Solis. Um, Today I'm going to talk about the paper, which is the title of the paper is a proposed bidirectional three-level DC to DC power converter for applications in smart grids. Um, okay, so first, what is a DC to DC converter? Um, Basically, it's an electronic circuit or electromechanical device that converts a source of direct current from DC from one voltage to another voltage level. It's basically a type of electric power converter. It's used on portable electronic devices such as cell phones, laptops. Basically, they are used to change the level of the DC voltage if you want like higher or lower voltage than what from the input, then you would use a DC to DC converter. Um, there are several types. Right here you can see like the most used ones. There's the buck converter, which basically takes an input and lowers it. So you're always going to have on your charge um, a DC level that's lower than the input. The boost converter, which basically does the contrary, it takes your input level, your input DC level, and will multiplies it by some factor, or as the name suggests, it boosts the input voltage. Then there's the book boost converter, which is basically a combination of the buck and boost converter together. So it lowers or increases or decreases the input level voltage. And there's the cock converter, which basically takes it's basically the same as a buck boost converter. However, in theory, it has a ripple factor of 0. Um, okay, so the paper, um, the general topic basically talks about how the advantages and applications of DC lines instead of AC lines. Um, Basically, the main idea is AC is universally accepted for the generation of electric power and for its distribution to consumers. However, we're going to see later how sometimes, yeah, having a DC line is actually more convenient, depending, of course, on your on your uses. Um, in order to deliver power from generating stations to load centers and facilitate interchange of power between different power companies, voltages are stepped up to transmission levels. Transmission lines have one or two sets of three-phase AC conductors suspended from towers. And sometimes, like I said, depending on the use, underground or submarine cables are used less frequently. In some cases where the additional cost is considered justifiable for technical or environmental reasons. Like we're going to see later, also you can use submarine lines. You have to sometimes use submarine lines when you're trying to connect um, different landmarks, uh, as let's say France or London. Um, so the rationale in the paper, well, it's different ideas. So a DC line with two conductors is cheaper to construct and often has a lower power loss than a three-phase AC line rated for the same power. Um, of course, in AC you gotta have at least three lines. That also, I mean, that immediately suggests that you're gonna have an extra cable that you have to like use instead of when you're talking about DC, which only uses two cables. That this becomes well cheaper when it comes to the price, of course. Moreover, the same DC line is often considered as equal in reliability or of service to a double circuit three-phase line. So, like I said, um, you have to pay more if you wanna use AC lines because well it's one more cable basically. Um, the economic advantages are proportional to the line length, but are offset by the substantial cost of the covering equipment. Um, just based on this fact, there would be a break-even distance beyond which DC would be actually cheaper, um, several hundred kilometers for overhead lines, and much less more costly undergrounds and submarine cables. So there's like a distance that you have, I mean, that after which the expenses become less. All right. If the AC frequencies at the converting stations are nominally the same but controlled separately, their frequency independence is maintained by the DC link. In other words, the DC system is an asynchronous link. So of course in DC you don't have to have I mean you don't have to worry about a frequency. Um, for example, in North America, they operate at 60 hertz, and in some parts of the world they use 50 hertz. Um, and on occasions, there's a need to actually interconnect systems which have two different nominal frequencies. So in Japan, um, there's two countries, yeah, two cities, because of cultural reasons, like historic reasons. Um, they use two different frequencies, 60 and 50. So they do have to have a station that converts like well 60 to 50 hertz, of course. As well, some applications that the paper talks about. Um, so long distance overhead DC lines conveying bulk power from remote generating stations to load centers, such as in Itaipu, Brazil. Um, the dam includes 20 giant turbines. In 1994, the dam was named by American Society of Civil Engineers as one of the seven modern wonders of the world. Um, General Electric, renewable energy, they were the ones who manufactured 10 of the turbines, and it includes it produced 79.44 million megawatts of power in 2019. So it's actually a lot. Um, Another application is the long distance seasonal or daily power interchange, such as the Pacific DC inner T linking or Oregon with Southern California. Um, so this, well, Path 65, as they call it, is an electric power transmission line that transmits electricity from the Pacific Northwest um, to the Los Angeles area using high voltage direct current, so HVDC. Mm, the line capacity is 3,100 megawatts, which is of course a lot, and it's enough to serve 2 to 3 million Los Angeles households, and represents almost half of the Los Angeles Department of Water and Power, electrical systems peak capacity. All right, another application is the submarine cables, such as the Cross Channel 2 between Great Britain and France, like I said before. Um, so it's basically a submarine cables, which is a 550-kilometer subsea cable with a 149 submarine segment. And the first fiber optic subsea cable to be built across the entire channel in nearly 20 years. Another application in the US also is the zero distance connections, back-to-back schemes between adjacent systems such as Miles City in Montana. This converter station is a high voltage direct current, so HDBC2, back-to-back tie that provides a connection between the US Eastern and Western electrical grids. Alternating current from one side, it's transformed into universal direct current, which is also transformed again to match the AC frequency to the other side. So basically, um, what I said about Japan before, it's basically being used here in the US actually. So allowing two of the America's three electric grids to balance power resources, also share energy reserves, and provide system operating flexibility. And the last one, the last application is the underground and undersea DC cables, such as the Cross Sound DC link between Long Island and Connecticut. The Cross Sound cable is a 25 or 40 kilometers long bipolar high voltage direct current submarine power cable between New Haven, Connecticut, and Shoreham on Long Island in New York, of course. Yeah, that's it. I hope you liked the video. I hope you find it helpful. If you want to like take a look at the paper, I'm gonna leave a link below. Well, so you can just, I guess, watch it, well, read it. Thank you.